Good morning, dear student. I am Rupak Shah from the Millennium School, South City, Lucknow. Today I will be taking you lecture number 4 for the chapter Magnetism. Before I start today's content, there is a small recap that what you have studied in the last video. You have studied about the solenoid, a long coil made up of large number of insulated copper terms on a suitable core materials. You have seen that field lines resemble to the bar magnet, which looks like a closed curves. Also, you have seen that magnetic field of the solenoid depends upon number of turns, current given to it, and nature of core material. Along with that, you have also studied about the magnetism or electromagnetism in straight current carrying conductor and circular loop, and the factors on which their magnetic field B depends upon. You have to study their field lines very carefully. I told you some methods to draw the field lines with the help of compass, and always remember the methods in which the field lines are constructed for all the three. First, straight current carrying conductor, second, circular loop, and third, solenoid. They are commonly asked in examination, and their field lines has to be practiced. So today we are starting with the basis of making a strong electromagnet. It is connected to the solenoid only. Actually, I told you the nature of core material. If the core material is taken the soft iron, then it will become a temporary magnet or an electromagnet. And if you are taking a core material hard, just like alloy, then it will become permanent magnet. So dear children, here we are going to make a strong electromagnet. So if you want to make a strong electromagnet, this core material should be taken of soft iron core, and that should have a large number of insulated copper turns, just like in the solenoid. But can you see what is the shape we have taken? The shape which we are actually looking into at this moment to make a strong electromagnet is U-shaped or horseshoe-shaped magnet. So this magnet that you are seeing in the diagram is actually called U-shaped or horseshoe magnet, and it is a basis for making a strong electromagnet, because here we are keeping behind three factors in our mind. That is, to make a strong electromagnet, we have to take a soft iron core first, and its magnetic field will depend upon three factors. First, as usual, number of turns. Second, again I told you it is a basic thing, that is current. So these are the two factors which is normally depending on the coils. And third factor, which is air gap between the magnetic poles or a terminal. Now air gap is so important because air gaps, there is a large number of air molecules, and if this gap is too large, then what will happen? It will start making the friction or cause a resistance, and due to the resistance the current will decrease, and if the current decreases, then your magnetic field decreases. I will just show you, because suppose we take a electromagnet in this way, and if you make a large number of coil, there is a too much gap. But if you take any electromagnet in U shape, the gap reduces between the poles. So here you can see this pole and this pole, there is a large amount of gap. So instead of decreasing the number of coils, what we have done, we have just twisted it in the form of U shape, so that the number of coils remains same, but the gap between the terminals is reduced. So if you reduce the gap between the terminals, what is happening? Your air gap, or the air friction is reduced, and as a result the current is increased, and if the current is increased, it is going to make a strong electromagnet. So dear student, please follow that. If you want to make a strong electromagnet, you have to take the shape, not a long, we have to take a shape in the form of U-shaped or horseshoe shape. I hope it is clear. Horseshoe shape means it can be a little bit like this. It is a horseshoe shape. So it is generally U or horseshoe shaped magnet only. So you can understand the utility of that. Why we have twisted in the form of U shape or a horseshoe? Because we want to reduce the air gap, and if it is reduced the air gap, then easily we can see that it is making a strong electromagnet. And the material that we have taken is soft iron core. So I hope this topic is clear to you. I told you many times that whenever you see any topic, at least watch the video for 2 or 3 times and try to understand the notes also. So read the notes also. You will find that there will be no difficulty in understanding the content. So now we are moving to the new topic that is called force due to current carrying conductor. What is the force exerted on current carrying conductor? Dear student, I have made one setup. You can easily see that I have suspended a straight current carrying conductor, although it is not carrying at this moment. So this is a straight conductor which is being coiled and then suspended with the help of support, and it is connected to the cell or a battery with the help of switch. Here you can see a bar. It is a magnet, which is a horseshoe magnet, but it is a permanent magnet. It is not an electromagnet. यहाँ पे हमें एक strong horseshoe magnet लेना है और उनके पोल्स के बीच में हमें इस रॉड को या स्ट्रेट कंडक्टर को रखना है जो सस्पेंडेड है, फ्री टू स्विंग है. So I am reading the activity in front of you. Here in the experiment, a straight current carrying conductor is placed between the poles of U or horseshoe magnet. It is a strong one. This experiment is actually trying to say that this particular conductor is going to swing, and due to the force exerted by the magnet on another magnet. Because when we start giving the electricity to this particular straight current carrying conductor, it also becomes a magnet, and this is also magnet. So what will happen? Magnet starts giving the force, and that force starts making the swinging. So I am just reading once again that here, I am continuing from here. This experiment shows that this particular conductor is free to swing and connected to the DC source cell or battery with a key. And when we switch on the current, it starts swinging. Now, reason क्या है? Due to the force exerted by the U-shaped magnet on current carrying conductor, which becomes also a magnet. So magnet आपस में force लगाते हैं, and as a result, due to that force, they start swinging in a particular direction or like a swing. So I hope this experiment is clear to you. I'm just explaining once again that this straight conductor is kept between the poles of strong permanent magnet, and as soon as we start the current in this straight conductor, it starts swinging due to the force experienced or a force exerted by this permanent magnet. So this also becomes a magnet, this also magnet, and as a result, which is free to swing, it starts swinging due to the force. Now here the force which is exerted on the current carrying conductor depends upon some factors. The first factor is magnetic field, because it is experiencing a magnetic field due to U-shaped magnet. जो पहला तो फैक्टर क्या है, जो मैग्नेटिक फील्ड हमने इसको दिया है, किससे दिया है? यू शेड मैग्नेट के बीच में रखा है, तो वो फोर्स मैग्नेटिक फील्ड उसके ऊपर डिपेंड करेगा. सेकेंड फैक्टर जो है वो दैट इज कॉल्ड द करंट. ऑलवेज आई हैव टोल्ड यू दैट फोर्स डिपेंड्स अपॉन करंट ऑल्सो. सो जो करंट आपने किस में दिया है, करंट उसमें स्ट्रेट कंडक्टर में, उस पर भी डिपेंड करेगा. तो टू फैक्टर्स, फर्स्ट मैग्नेटिक फील्ड, I current that is being given to straight conductor, and third is called the length of the conductor, because if we increase the length, current also increases, and if the current increases, force also increases. So combining all the three effects, F is directly proportional to BIL. P is magnetic field, I is current, L is the length of the conductor. So if you remove the proportionality sign, it becomes KBIL. K की जगह हमने 1 डालना है, because the value of the K is 1. So your standard formula for F becomes BIL. But as for the working formula, which is not in your syllabus, but you can understand that F is equal to BIL sin theta. We have applied the trigonometric function is that if theta is 0, if you put the theta 0, sin 0 becomes 0 and your force becomes 0. I will tell you this in example after giving on rule. And if theta is 90, sin 90 will be 1 and your force will become maximum. It means if you are having an angle of the conductor and the current, or you can say the magnetic field, is 0. I will make you understand this after the rule. So the force exerted will be 0 and this your rod will stop swinging. But जब थीटा 90 डिग्री होता है तो जो रॉड और मैग्नेटिक फील्ड इनके बीच में जो एंगल बनता है वो दैट इज 90 डिग्री एंड एज अ रिजल्ट द फोर्स एक्सपीरियंस्ड इज मैक्सिमम BIL. So just to understand this particular thing, you have to just remember that conductor is placed perpendicular. If your conductor is placed perpendicular to the magnetic field lines, then it is going to be the maximum. So we are applying one rule that I have made here. That rule, I will tell you what rule that is called. That rule, you can easily see that we have stressed the three things: thumb, forefinger, central finger, all mutually perpendicular to each other. And when we place all of this particular thumb, forefinger and central finger mutually perpendicular, this is 90 degree, this is again 90 degree, and again they are all 90 mutually perpendicular to each other. Then this rule is called Fleming's left hand rule. And this rule will be applied for electromagnetism. Fleming's left hand rule. Force, your magnetic field and current. I've given a small thing that to remember: father, mother, child. Father is F, force; mother, M, magnetic field; child starts with the C means current. So in this way you can remember all the things which are the terms given to them. Force, father, F से start हुआ है, mother M, magnetic field and C. So all these are placed mutually perpendicular to each other so that thumb shows the direction of force, forefinger shows the direction of magnetic field, and your central finger shows the direction of current. So I hope you can understand this rule. We'll be more clear about this rule in the next video, how to apply them and how to understand them. We are just making you more clear from the particular formula. If B and I, if the magnetic field and I are parallel to each other, if B and I, or you can say the length of the conductor, are parallel to each other, what is the angle made? 0. So in that case, if your conductor and the magnetic field are mutually parallel to each other, then it will not swing, no force is experienced, so your force will be 0. But I already told you, if the current or a length of conductor is perpendicular to the magnetic field line or a magnetic field, in that case sin 90, and sin 90 is 1, so you get F is equal to BIL, and this is the maximum force that any conductor can experience only when the current or a length of conductor is perpendicular to the magnetic field. So this particular rule should be clear to you. Please observe the video for 2 or 3 times. I told you, read your NCERT chapters, NCERT content also, and I told you many times that if you have any queries, please contact us, give us your queries in writing, in a WhatsApp or anything, so that we can clarify it. And in the meantime, we can come in some doubt clearing session in the Zoom also shortly, and in that case we will be taking your problems or taking your rules in details if you want. Anyway, thank you so much. This is enough for you, and stay safe.